Okay, um, I'd like to show you something briefly about the graph format that I'm working on. So, here is a KDB graph format file that where I ran the program with a K of 8. So these are 8mers in reference to the C. diff genome. These are kmer IDs for 8mers, and I've recently patched the ID to kmer and kmer to ID functions. Here I am adding in that 61068 ID and then explaining to this function that the choice of k has been 8 because 61068 would identify a different kmer under a different choice of k. In this genome, this works out to TGT, GGATA. And then I'm saying that because these two are adjacent, you'll also notice that the last node in this link is the first node of this link, and so on and so forth. In fact, let's just convince ourselves that let's go ahead and convince ourselves of this, that the first eight letters of the C. diff R3 genome are TGT, GGATA. TGT, GGATA. Okay? That was pretty quick, so let me mouse over it one more time. Okay? So the Clostridia difficile R3 genome starts with the sequence that we claim that it is. You can also notice that in this sequence, the k-1 mer, or the 7-mer, GTGGATA, is the last 7 letters are the first 7 letters of this next one, which we said were adjacent. So that's proving that's not proving anything, but it's showing that the data that the IDs that we're using are consistent, and the claim that I've made, this is somewhat of a graph format, is representing kmers that have adjacency in nucleotide space, not numerical space. That's all that's saying, really. So you can assume that if you were to add FASTQ files or other data into a single graph, then you would get an adjacency list from this format, and it would tell you at least what kmers it's found that are consistent with respect to one sequence, and then from that you could do graph traversal and collapse at some point in the future. So at some point in the future, I'd like to add graph traversal as part of the De Bruijn graph features of this program. I also want to just go over a few functions. The most important one is profile because it creates the count vector. The graph function is operational. It also works on FastA or FastQ. I currently have a minimizer function that I'm using to describe whether or not a particular kmer in a sequence of kmers is selected as a minimizer at some fixed length across the sequence. So every 100 base pairs, you pick a minimizer. Every 10, whatever your choice is. And then you can use these minimizers at some point for Smith-Waterman alignment. I also have this usage command that's somewhat new that gives you some description of the things that are going on with this particular subcommand. So for example, we see the name here is called profile. It's the name of the subcommand. A short description of what it does, and then some other descriptions. This is the usage of the subcommand. You set k to some value. You use some string as your output prefix, and then you add some FASTA data or FASTQ data, and it will produce profile1.12.kdb for kmerdb, KDB. And then it'll also produce some stats at the end of it. You can see that the number of nullimers plus the number of 12mers should add up to the theoretical 12mer count. This is the total number of kmers processed in that file. And this is an example of the YAML header that gets produced. And then kind of a table. It reiterates some of this stuff again. It describes certain key parameters, key inputs. This is outdated. I'm using the -o, as we can see here. I'm no longer making that the last positional argument. And then a description of some of the things like arguments, inputs, features. So what this program does is it creates a count array as the sequences are read by a sliding window. It supports both compressed and uncompressed .fa and .fq, or .fasta and .fastq. My short name for this feature is parallel OOP sliding window kmer shredding. The next feature is that the kmers are tallied and metadata are merged across the input files. Short name is merge the counts and metadata from across the inputs. Alright. This is the steps in the program. First you read everything into an array. Then you collate the count array, just like I mentioned. You merge the counts. Oh, so collating the count array, this is within one particular FASTA or FASTQ file. If you have multiple sequences in the FASTA or FASTQ, that collate them into a single count array, and then aggregate counts across all input files. So that's why that's a distinct. This is why that's slightly different than this. Then you print the final stats and you close the output. I call that metrics and shutdown. Every program has a timer to show you how long the program ran, and some closing stuff. So this is, you can see this is different information than you would get from running the help command. This is the usage statement. You can use verbosity flags, a choice of k that is required. You can also alternatively choose a min k and max k, and it will run the program across all choices of k that are between min k and max k. There's a required argument called the output name, and it will name, so if your output name was example, and your min was 8 and max was 10, then it would produce example8.kdb, example.9.kdb, and example.10.kdb in the output directory, as well as the log file. It also writes the log to standard error. There's also a debug flag that's kind of useful. Anyway, so we're kind of getting away from the point here. Here's an example of the minimizer file. So this is the chromosome name. This is the length of that chromosome. This is a kmer ID within that chromosome. So really the sequence position. This is the kmer ID of the kmer at that point in that chromosome. And let's convince ourselves of this. Let's make this 700. Actually, let's make it 705. What the hell? Okay, so cool. This whatever genome this came from, it is an off by one indexing issue, but these are the kmers in that particular organism. So I should note that. It needs a bug fix. And the last column is 0 or 1, depending on whether or not this particular kmer should be chosen as a minimizer. These occur at regular intervals. And that's possible with the minimizer command. So I'm still working on that. Minimizers help. So this takes a FASTA and a KDB file associated with that FASTA, and then a window size, and produces minimizers for that. I mentioned usage and help. They're the same command. They're distinct from the argparse-h. The alignment function isn't working yet. It's still a work in progress. So it's in there. The matrix command is something that will aggregate count vectors into a count matrix. So let's take a look. Only going to keep you for a little while longer. There's a bunch of different 8mer profiles that I've made. One of them is from 0.6.3. It's from an older version of kmer. So if I run kmerdb matrix from, it's going to take all the count vectors and aggregate them into a table. It took about 5 seconds to run. You can also pipe this directly into, and I haven't tested this, so this will be interesting, distance, Pearson, standard in. So you can pipe it through to the distance command, and it should produce a correlation matrix. And it should use my Python Pearson correlation coefficient. So it took 5 seconds to aggregate that, and it should be, there it is. So this is a correlation matrix. Here are different acetobutylchem strains, and most of them are pretty similar. So they've got this 0.57, 0.97. So these are acetobutylchem strains with respect to other acetobutylchem strains. This would be B subtilis to other acetobutylchem strains, other Clostridia. They're more distantly related. Last column is E. coli, so that one's this. It's down to 0.46. So it's much more distantly related. The C. acetobutylchem strains and other Clostridiales, are all very similar to one another in terms of their kmer count profile. So that is piping a count table aggregating from the count vectors, producing the count matrix, piping that to the Pearson correlation coefficient, and using standard in to accept that input and producing a correlation matrix. There's other functions in here. Hierarchical clustering, k-means. At some point I'd like to revisit this, shuffling the k-mer count vector to see, to take a look at the noise. There is an index feature that essentially permits to some degree an on-disk indexing into some of this data. And I'm not sure if I have some larger files in here. Here's a 12-mer profile, and you can see it's already up to 82 megs, whereas the 8-mer profile is only half a meg. So it does scale quite a bit, and let's try this. Let's do k of, why not 17? Because I'm feeling loosey-goosey. Test.17.kdb. Test. Let's do E. coli. Matter of fact, we will view it with verbosity and the debug options. So, one last little thing. There's some citation information at the top. You can silence it if you want to by running that command. It's got the current version of the program that's running, written in the header, and then a little usage information. This is how to use the profile command on fastIR.fastQ inputs. This is how to collate count vectors into a count matrix. This is that Pearson correlation coefficient that we saw. And similarly, this is running these two steps as a single piped command. There's also k-means clustering with BioPython or scikit-learn, and hierarchical clustering, as well as t-SNE and some other stuff. So this is the number of k-mers that were identified. Let's take a look. It's running at 2.1% of my CPU and hogging about 33% and climbing amounts of memory. Wow. This is going to crash things out pretty soon. Even on just K of 17. I don't use any special tricks with this. So yeah, this is gonna fry my computer soon. Shit. Stop. Stop hogging all the RAMs. Fuck. Are you serious? Okay. Should be stopped now. Cool. Alright, let's try it again with 15. This will work. I've run this before. So the reason I'm showing this is I've got 125 gigs of memory on my machine. part of the point is that the memory usage of a simple kmer counter can become very large because you're storing how many? I don't know. Let's find out. How many kmers, IDs, numbers are you storing? 4 to the 15th. So 1 billion at k of 15. That's not that bad. There's some redundant stuff that ends up getting stored, and that's why it ends up taking a lot. This, on the other hand, just changing it to 17 is already up to 17 billion. 17 billion elements in each numpy array, and there's some redundant information. We can see it climbing again. Here it goes. It'll plateau though. I'm sure of it. I've run this one before. It doesn't have leaks or other stuff. It's just a Python program. And it's already read 222 megabytes, but then it is there. It looks like it's stabilized. 43%. No, here it goes. Still climbing a little bit. This usually takes, cool. It's finished counting. Now it's dumping stuff to disk. We'll see how long it took to run on K15. So it can run really fast. This does follow IUPAC standards. So it counts certain letters in nucleic acid FASTA files as doublets or triplets. There are certain residues that do that. And it will add a count for both. It's a simple and easy solution. It treats N residues as ambiguous and essentially creates somewhat gaps in the kmer profiles, which is sensible behavior. So if a kmer has an N in it, it doesn't get a kmer ID and it doesn't get included as any count. Doublet or triplet residues, if you have ambiguity in your sequences, it will count them as both. That seems to be a sensible solution as well. It's not great. But this is fundamentally just kmer counting. It has nothing to do with graph assembly and other stuff. So the process has been run. It doesn't have... Let's see. This should be Xing soon. So this was the argv. This is what the program was run with. It's got the path to the executable, the subcommand, the verbose arguments and debug arguments. Here's the command that we actually ran. You'll see it's the same thing. -O with our output and it'll append .15.kdb at the end of this. And it's running on MG1655. While I have you here, I'll bring this to the forefront. I recently patched the kmer module. So here's the doublets and triplets stuff that I was talking about earlier. So these are triplets. This is the nucleic acid B in IUPAC standard, and it could be either C, G, or T, but not A. Similarly, the doublets. And the ambiguous character N. There were some issues related to the definitions of these being public or private, as well as constants in the kmer module. Those are fixed. I'm still using... Cool. Is that consistent? So that was the number of nullimers. This is the theoretical kmer number. Was that consistent with what we set up here? I don't know. Well, that's the number of 15 mers. It's oh yes, it was. Here we go. 4 to the 15th. So this is the total number of kmers that were processed from the input FASTA file, which in this case was E. coli. So again, back to this. Most of these modules have doc strings with description of the parameters and return types. That's not stuff most people use. This one is. So the bit shifting trick that I'm using is used by everybody and their brother throughout the throughout the literature about the bit shifting trick, or in kmer count vectors. And so I'm arbitrarily giving credit of this to Anvar, who authored kpal, which was an earlier predecessor Python library in the kmer space. Alternatives to jellyfish. Similar things include Khmer, and some online and probabilistic Bloom filter stuff. But what this function does is it takes some string, a kmer, and converts it into the quote-unquote binary encoding using the bit shifting trick. Here we go. Bada boom. Woof. So here is a kmer. This is the 217/890th kmer. These are abundances. This is the so some of those are empty. You see some of them are empty. They're just rolling with zeros, meaning that they were nullimers. They're not present in that organism. Other ones might have one count, and so therefore the total fraction is to the 7th power. It's an incredibly small percentage of that genome. And there's a sort feature that will allow you to sort by the most abundant kmers if need be. If you really need me to put that in here, you know, it is. But essentially, this is a tabular format. You can do all of this in Excel or the command line. You can sort based on the kmer abundances that you're interested in. And so all these numbers that are incrementing, those are kmer IDs and column numbers. Or sorry, row numbers. Okay, so I'm back. Program ran. I was looking at KF15. So, as I mentioned before, there's approximately 1 billion 15 mers. The total number of kmers that were processed was this. The number of nullimers, or zero count kmers, was quite large. Summing that, 61 billion 69 million with 4 million actual 15 mers. Unique 15 mers reveals or adds up to the theoretical count. It's also worth noting, let me get rid of the log because it's embarrassing how long that is. Pass scratch test eco log. Yikes. Okay, so I mentioned before that for some other KDB files, they can be quite large. And I think I removed most of them the other day. Yep, great. In the previous video, because they were taking up a lot of space. In the previous video, I mentioned that the 8-mer profiles are ridiculously small, just a few dozen KB. 12-mer profiles, including the compression, can get up to several megs. However, this 15-mer profile, when compressed, because there's a billion, gets up to 5G. So that's a considerable amount of data to load into memory on a laptop. It's also just a lot of, zeros, essentially, because if we use the head command or or the view command, whatever, or zcat. Hello? Okay, autocomplete doesn't work. And then if we look at the first 50 lines of the file, you can see that most of them are zeros. This is again, a reminder, the leftmost column is just a column ID. The second column is a kmer ID. And this has to do with the way the indexing and bit shifting has to do. It's not a, UUID or something, arbitrarily chosen. It's just a numerical representation converting the sequence. So this would be all A's, and actually we can go to the shell and take a look at what that would be, and it's all A's. So from kmerdb import, what is it? From kmerdb import kmer, and then if we do id to kmer 1 0 with 8, it's all A's. So this would be a very odd kmer indeed to see. And if we increment, we're not getting very interesting kmers. Obviously somewhere else down in the file, Anyway, if we look at 500, for example, we're still not getting anything interesting at all. But if we grep for non-zero, grep v 0.0, and take a look at the first 500 of those, most of these are unique non-nullimer kmers that have exactly a count of 1. So this was with k of 15. You can see that the data is getting very sparse and very binary very quickly. Not as much. So basically it means that what that means in the real world to biologists is that if you're a biologist and you're studying a bacterial genome, choosing k in an assembler that's arbitrarily high, like 22 or 25, is not only going to be a waste of your computational resources and a waste of time, but it's also going to provide a signature sensitivity in the kmer in the kmer space that isn't necessary. So you're much better off running your program with a more appropriate choice of k. However, for organisms like human, certain trees, plants, animals that have larger genomes in the billions of base pairs, selecting a choice of k larger than 15 can be advantageous, or even as small as 15 would be computationally advantageous with not necessarily any loss or deterioration in signal. That said, going down to 6 or 8, a 6mer doesn't provide much unique information about that kmer or the organism that it came from. So there's different sensitivities about all this kind of stuff. Alright, so again, just to reiterate, the important thing to note here is that when you choose k as large as 15, it produces huge memory requirements. There is no cap or boundary in kmerdb on the amount of data that you can throw at it or the choice of k. It's a very simple program. And so 5 gigs of data compressed is actually quite a lot of data. You can see that it's blocked GNU-zip format, BGZF. It's zlib compatible, so you can use zcat instead of cat in order to inspect the contents, or you can simply use the kmerdb head or view commands. I think it's header, kmerdb header. Header. So let's take a look at that one more time. Well, this it works, but I'm guessing that it's trying to read way too much of the file. Stuff that isn't necessary because it doesn't necessarily know how many blocks to read. You could handle that in the header, but I'm not worried about it. The header function is really only supposed to slurp the header, and I thought that it did, but it looks like it's doing some reading. So here is an example again of the log output. This is verbose logging. This was with very verbose, so running this on quiet would take much less time without verbose logging. I keep the debug flag on sometimes for development, uh, in ideal behavior, my keeping my debug flag off, not including the debug flag in the invocation, would provide some very useful things to the user. Potentially the step of the program that malfunctioned, which can be useful for me rather than just giving me necessarily only the stack trace. The functionality is supposed to present you with the part of the program uh, by virtue of the AppMap module that will kind of pinpoint which step malfunctioned and keep log of that throughout the program. It'll give you the last 20, 50 lines of the log that it knows what was going on. That's probably why the memory usage has been up so much, because it's keeping all of the logs instead of just the last 50 or whatever. Maybe I should patch that. I might make a GitHub issue right now. You can see an invocation here. If you have issues with the log as it currently stands, you can write it to dev null. You can turn the verbosity features off so that it's not spilling that standard output, standard error. The quiet will help also reduce the output of the program. Setting k to smaller k's results in faster runtime, and yeah. That's all I have. Thanks for watching.